An elementary matrix is an identity matrix that has undergone a single row operation. Recall that row operations include adding, subtracting a multiple of a row to another row, multiplying a row by a constant, or interchanging a pair of rows. It's like programming a row operation into a matrix. We can multiply that matrix to a target matrix to effect a row operation. This would have the same effect as if we just directly apply the row operation onto that target matrix. Given these two matrices U and V, we have to show that U and V are equivalent matrices, meaning that we can use row operations to turn U into V or vice versa. To demonstrate that, we have to find a matrix A so that V is equal to A multiplied to the left of U. We're also asked to express A as a product of elementary matrices. The strategy is to use row operations to make U into V. Every time we apply a row operation, we have to apply the same row operation onto an identity matrix. But what dimension of identity do we use? Since the matrix A is going to be left multiplied to U, the dimension of A, and therefore the dimension of the identity matrices, have to be compatible multiplying to the left of U. U is 4 by 3. Remember, with matrix multiplication, the what I call inside dimensions have to be the same. So then that has to be a 4, and since identity matrices are squared, it has to be 4 by 4. A is 4 by 4. Therefore, these elementary matrices will also be 4 by 4. Now, how do we go from U to V? The row 1, 2, negative 4 seem to have switched places with 7, 0, negative 1. Interchange rows 1 and 2. We also interchange rows 1 and 2 in the identity matrix. The next thing I notice is we have the row negative 5, 0, 1 versus negative 10, 0, 2. It looks like that row has been doubled. Multiply row 4 by 2. In a new 4 by 4 identity matrix, we're going to multiply row 4 by 2. Remember that an elementary matrix only has a single row operation, so we can't carry over that elementary matrix from the step before. It has to be on a new identity matrix. U and V looks really similar now, other than that row 1, 4, negative 8, compared to V, which has 0, 2, negative 4. How do we make that 1 into a 0? We can subtract that 1 with the other one to get a 0. So 4 subtract 2 gives us the 2 that we want, and negative 8 subtract negative 4, which is negative 8 plus 4, will give us that negative 4. Let's go row 3 minus row 2. In a new identity matrix, we also go row 3 minus row 2. To get matrix A, multiply together the elementary matrices in the order that we did them. E1, E2, E3 going toward the left. We can check our work by multiplying together A, U, and seeing that we do in fact get V. Here are some things to keep in mind when doing these types of problems. Make sure the identity matrix, and hence the elementary matrices, are compatible for matrix multiplication. Also, the order of multiplying together the elementary matrices. Since we're multiplying toward the left, we have to go E1, E2, E3 for these 3 steps, from right to left rather than from left to right. This may seem a bit counterintuitive, but it's because the matrix that's closest to matrix U is the one that gets multiplied first. In this case, it's E1, the first step that we did. And then it's the second step, E2, and the matrix that's farthest away from U is the step that we did last. Also, there are different combinations of row operations that can make U into V. What we did here is just one of these ways. Even though there could be different elementary matrices and different combinations of them, we would arrive at the same matrix A. Here's a good place to continue our list of equivalent statements. There are 2 new ones in this lesson. We can express the matrix as a product of elementary matrices, and the reduced row echelon form of this matrix is the identity. Let's verify these statements using the matrix A that we found. We are able to express A as a product of elementary matrices. Let's see if the other equivalent statements also hold. Verify that the determinant of A is non-zero. Cofactor expansion along the second column, 1, and then attach on that negative sign associated with that position. Cross off the row and column that has the 1, and then find the determinant of that. Cofactor expansion along the first row. We have a 1, and also the plus and minus sign associated with that position happens to be a plus. Cross off the row and column that contains the 1, and then get the determinant of that. AD minus BC, 1 times 2 minus 0 times 0. The determinant is -2, it's non-zero, as we expect. Next, we verify that A is invertible, and at the same time that the reduced row echelon form of A is the identity. We can try to invert A by augmenting matrix A to the identity matrix, and then row reducing. If A is invertible, then we expect the A side to turn into the identity matrix. We can interchange rows 1 and 2. Get rid of that -1 by adding to 1. Row 3 plus row 1. The 2 can be turned into a leading 1. Multiply row 4 by half. And we see that the A side does turn into the identity, and the side that used to be the identity is now the inverse of A. We're able to verify that yes, the reduced row echelon form of A is the identity, and that A is invertible. Here's another example, with letters. Similarly to example 1, we're given a matrix, in this case X. We have to find a matrix so that when we multiply this matrix to the left of X, we get this matrix Y. We have to figure out the dimensions of this matrix A. X is 3 by 4. Since A will be on the left side of X, A will have to be something by 3 in order to multiply X. We're told that A is invertible, therefore A would have to be a square matrix. A is 3 by 3. We're also told to express A as a product of elementary matrices. Again, just like with example 1, there's no fixed way of solving these type of questions. We have to get X into Y using row operations, and at the same time apply these row operations to identity matrices so that we get elementary matrices. The first thing I notice is the S minus O, T minus P, U minus Q, and V minus R in the second row. Let's go row 2 minus row 1. To get the corresponding elementary matrix, we take the identity, in this case the 3 by 3 identity, and apply the same row operation, row 2 minus row 1, and we get our first elementary matrix. Let's call it E1. The next thing I notice is that in X compared to Y, it looks like rows 1 and 3 are swapped. Let's do that. Let's interchange rows 1 and 3. To get the elementary matrix, we take the identity matrix, and interchange rows 1 and 3 to get the second elementary matrix, E2. The next thing I notice is that row 1 is multiplied by -1/2. And now we have turned matrix X into matrix Y. To get the elementary matrix for this row operation, we take the identity matrix and apply the same row operation. -1/2 multiplied by row 1, and we get the elementary matrix E3. We multiply together all of these elementary matrices in the correct order, E3, E2, E1, to get the matrix A. And we can check our work. If we multiply A to the left of X, we should get the matrix Y. Here's a shortcut. The first row of A is 0, 0, -1/2. What it says is, in the first row, we're going to multiply the last row by -1/2, and then put that as the first row. So -W/2, -X/2, -Y/2, -Z/2. The second row of A is -1, 1, and 0, which means take the first row, multiply by -1, and add it to the second row. Another way of thinking about this is take the second row and then subtract first row. And this is the result that we get, S minus O, T minus P, U minus Q, V minus R. The last row of A is 1, 0, 0, which means we're going to put the first row of X as the last row. The first row being OPQR is now the last row, OPQR.